Okay, so last section we will take a look at in Chapter 5 is 5.5. It's on, I think, 3 different things. We've got the change of base formula, transformations of logs, so we'll go through that like we always do, and then graphing logarithms. All right, so on the calculator, what are the 2 bases that the calculator can do for us just by pressing a single button? Yeah.
10 and E.
Right. So if I type something like log 12 and ln 35, which one of those is base 10? Yeah?
Log.
The log.
Yeah.
And the ln is base?
Natural log.
That's the natural log, and the base is?
Like 2 point something.
Yeah, what do we call that number?
E.
E. Yep. We call that number E. Now, if we wanted to do, let's say, something like this. Log base 3 of 14. Okay. Do we have a button on the calculator that we can directly just press that button and it does base 3 automatically? Okay. Yeah? No. So we got to type that in a way that we can use one of the bases that we already have a button for. So when would you even need to do something like that? Well, let's say we have this. 2 to what power gives me 15. All right, well, we can kind of figure out what it's between. What do we know x would have to be between? What 2 numbers, yeah? It has to be between 3 and 4, because 2 cubed is 8. Well, that's too small. 2 to the 4th is 16. That's too big. So it's somewhere between 3 and 4, maybe 3.8, 3.9. A logarithm is going to allow us to figure out exactly what it is. The way we're going to have to do it is change this into log form. Okay, well, let's do it. So log. What's my base? When I change that exponential equation to a log equation, yeah?
2.
Yeah, my base is going to be 2. And what did we say last week? Logarithm always equals what kind of number? Yeah? The exponent. And the thing that was by itself, what do we call that?
Argument.
That's the argument. So if you can figure out how to type that in on the calculator, then we can figure out the answer to 2 to what power equals 15. Right? And that's what I'm going to show you how to type in. Now, the only thing that's making this equation hard is the fact that there's a variable in the exponent. Well, we had a rule that we could take exponents and we could move them in front. But in order to be able to do that, what kind of equation do you have to have? Like, you can't just take that x and put it in front and say x times 2 equals 15. Can't do that at all. Yeah? Right. You have to have a log equation. So just like you can take square root of both sides, you can square both sides, you can take the log of both sides. So let's do that. Let's take the log of what's on the left. Take the log of what's on the right. Now, because this 2 to the x is an argument to a log function, what can I do with the x now? Yeah?
Can you put it in front of log?
I can put it
X log 2.
And then what would be on the other side?
Log 15.
Log 15. And now, how would you get the x by itself here? Yep. Divide both sides by log 2. So that's gone. And look at what we get here. It's the same problem that we just saw earlier. The only problem with what we wrote over on the right side is we don't have a way to type in base 2 yet. But look at what we have on the left. There's another way to find x, but this uses base 10. That uses a base we don't know how to type in. So let's call that box 1. Box 1 is equal to x. And box 2 is also equal to x. They were the same problem. So what else does that mean? If box 1 is equal to x and box 2 is equal to x. Yeah.
Then 1 and 2 are equal to each other.
Right. Box 1 and box 2 are equal to each other. So log base 2 of 15 is the log of the argument divided by the log of the base. That's how you type in a log that's not base 10 or e. We are not going to have to go through these steps in the middle each time. All you have to do is take the log of the argument and divide it by the log of the base. And that's called the change of base formula. Okay? That's kind of proving why it works. So you take the log of the argument and divide by the log of the base. The base, think about it as line paper like that. The base is lower, so the base has to go lower. It has to go in the bottom of the fraction. The x is above the line, so the x is above the line on that one. Now, when I did this on the other page, I did it with logs, base 10. You could also do it with ln's, and you get exactly the same answer. So let's try typing in that one then that we had. Okay, let's type in log 15 and then divide by log 2. Make sure when you do the change of base formula, you close your parenthesis. And is that about what we said the answer had to be between? 2 to what power would give you 15? Yeah, we said it was between 3 and 4. Closer to 4. So now if you take 2 raised to the 3.90689, I'm just going to round it, you get about 15. So that's the power you would raise the number 2 to get 15. Now let's try typing the same thing in with ln. Take the ln of 15 and divide by the ln of 2. 3.906, same answer. So when you do the change of base formula, you can do it either with common log or natural log. Right? And we always pick one of those two because that's what you have a button for on the calculator. Common log and natural log. Okay, so any question on the change of base formula?
In what situation would using log base 10 be better than natural log or vice versa?
I don't really think there's any situation where it would be better or worse. I think it's exactly the same thing.
Okay.
Yeah. Yep.
Why is there isn't ln log base e?
Yes, it is.
So why is log base 10 equal to the log base e?
Why do they come out equal?
Yeah.
I'd have to think about the proof a little bit. Why?
Because of how log base e is different.
As long as you use the same base, I mean, technically, if you had a log base 7 button on the calculator, when you do the change of base formula, you could do log base 7x divided by log base 7b. As long as these two numbers are the same, it's always going to give you the same answer.
It's just the e that's going off.
Yeah. What's that?
The logs are going to count.
Yeah, it's like the bases. It's like the bases. They cancel out on the logs. Now, if they were different, that would work. You gotta use the same thing in the top that you do in the bottom. Okay. Yeah. So if you decide to use common log for the whole problem. If you want to do natural log, that's okay, but do it for the whole problem.
Yeah, your calculators have blocks on them. Mine doesn't, so I'm able to press log base and just on my calculator and just do it.
Oh yes, yeah. That's because I want people to know the change of base formula, because we're going to need that for certain things in the future. So you're going to have to know that formula. Okay, so let's graph that. Log base 3 of x. Am I able to directly type a base 3 log in on the calculator? No. So I need to rewrite that in a way that I can type it. How can I rewrite that? I showed you two different ways. So I can put it in y1. Yeah? Yep. So we're going to just do the common log of x over the common log of 3, and we're going to graph it. Okay, the biggest thing that can mess you up is when you press the log button, it opens a parenthesis for you. You're responsible for closing it. So we got log x divided by log 3. It's very important you close the first one, not as important you close the one at the end because nothing else is coming after it. So there's our sketch. We talked a little bit about sketching logs last week. Any comments on that sketch? Yeah, thinking maybe?
It kind of looks like a square.
Oh, like a sideways parabola?
Yeah, or like a square.
Or like a square root?
Yeah.
Okay, so square roots have a start point and they go in one direction forever. Do log functions have a start point? No, that's not what it's supposed to look like. What's supposed to happen here that the calculator is not showing? Yeah?
This is supposed to continuously go down.
Right, we're supposed to have a vertical asymptote because there's no transformation shifting it left or right. We're supposed to have a vertical asymptote at the y-axis. So this should, and before I draw it, just look at it. It looks like it starts at -2, right? It really should keep going down. And if you zoom in where it looks like it starts, does it look like it's starting at -2 now? No, now it looks like -3. All right, so if I keep zooming in, I can see it go down further. It's just it gets too steep to be able to draw. Okay. So that's what it should look like. So now we can answer the question about the domain and the range. Is that what they want to know? Yep, domain and range. So let's start with that. Okay, what's the domain there? Yeah.
0 to infinity, not including 0.
So that goes from the y-axis and it goes to the right forever. If you try to plug in a negative number to a log, does anybody remember what kind of answer you get?
If you put the negative log or something?
No, plug in a negative number to a log, like log of -5.
Error?
Why? What kind of answer is that? Yeah?
It wouldn't be a real answer.
So what kind of answer would it be? Yeah?
Imaginary.
Imaginary. Okay, when you try to take the log of a negative number, it's not that you can't do it, it's that the answer would be imaginary. Okay? It's not real. Now, when you try to take the log of 0, you also can't do that either, but it's a completely different reason why. It's not saying that the log of 0 is imaginary. That's saying you can't even do it. And that's because there's a vertical asymptote. So the graph never hits 0. All right, so the domain is just 0 to infinity, open interval. How about the range? What's the range on that? Yeah? Yeah, so your range is going to be all real numbers. And it might not look like it's going to go up forever, but it does. Okay, there are no horizontal asymptotes in a log function, ever. Okay. It goes up. Well, how quickly does a log function go up? Does it go up fast or slow? Very slow. Right? Remember, for a common log, by the time you get all the way to like 100,000 on the x-axis, so go all the way to 100,000, you've only gone up 5. And it's going up, but that's slow. It's very slow. Okay. What else do they want? Domain, range, and a complete graph. So remember, complete graph you should be giving me the window. That's not the right window. I think I just did zoom 6. That's when I zoomed in. So give me that window. Oh. Give me that window. That's it. That window works. So any questions on typing something like that in because it's a base 3? Now, how would that compare if I typed in ln x divided by ln 3? What would the graph of y2 look like compared to y1? Yeah?
I can't do anything for that stuff. My calculator's getting an error. Invalid dimension.
Okay, so if you're getting invalid dimension, it's probably because one of the scatter plots is on. So that was from something somebody did last week. So just press the up arrow and go to the scatter plot. Hit enter and make sure your plot 1, 2, and 3 look just like that. If that happens to anybody else, that's why. All right, so back to my question. Y1 and Y2. How's it going to compare when I hit graph now? Yeah. Yeah, it should be exactly the same thing. Since I turned the scatter plot off and on, it's going to redraw everything. There's the first one, and there's the second one. Trace is exactly on top of that. Okay, so just proving there's no difference between the two. Okay, so transformations. Transformations on logarithms work the same as every transformation we've done all year. Okay, so let's just go through and at least say what they are. If you aren't sure about one of them, I would write it down. Make sure you know what it is. Well, let's start with A. Okay, what kind of transformation is A? Yeah?
Is it horizontal? Like you shift either left or right?
Yeah, it is a horizontal shift. Yep. If A is a positive number, which way does it shift it? Yeah?
Left.
Shifts it to the left. What about if A is a negative number? Yeah?
Right.
To the right. Yep. What about B? It's still inside the parentheses, but now it's multiplying instead of adding. Yep. Yep, that's your horizontal stretch or compression. If you put in a big number for B, what's a big number going to do? It's going to cause the graph to compress. So if you want to compress a log function horizontally, say by a factor of 5, do that. That's a horizontal compression by 5. What if you put in a fraction? Like 1/3, 1/2, like a positive fraction. Yeah? Yeah. That's going to do what? Yeah, it's going to stretch it. So if you want to stretch it horizontally by a factor of 5, that's what you want to type in. Okay, so B causes horizontal stretch or compression. That's it for inside the argument. Now we go outside. What's the C going to do? It's like B, but it's on the outside. Yeah. That's a vertical stretch or compression. If you make C a big number, what's that going to do to your graph? Yeah? Stretch. Bigger number stretches it bigger. Small numbers compress it smaller. So C is not backwards. All right? And what about D? It's adding like A, but it's on the outside. Yeah?
Vertical shift.
That's your vertical shift. And a positive number for a vertical shift moves it up. Negative number down. Okay. And then one more thing we need to mention that I always mention. What's the last thing you think I'm going to say? I've said it at least 10 times this year, yeah? If there's a what?
A negative. Instead of the C.
Or
B.
B, what happens?
If it's B, is it a reflection over the y-axis?
Yep, if there's a negative in front of B, that is a horizontal reflection, which is over the y-axis. And
And C is reflection over the x.
C is a vertical reflection if it's negative, and a vertical reflection is over the x. So you can have up to 6 transformations. 2 shifts, 2 stretches, 2 reflections.
So C does. Oh, I spaced out.
What does C do?
Yeah, I messed C. I only got A grade.
Somebody remind us what's C? Yeah? Which way?
It's a bigger number. Oh,
Vertical. So C is your vertical stretch or compression. And D is your vertical shift. And when we study trig functions, like sine, cosine, tangent, it's going to be exactly the same thing. We're going to have the A, B, C, D again. No difference. But this is the last function that we studied in the algebra part of the class, so we're not going to see transformations again until we do trig functions. But we will do transformations in trig.
I just was writing. I missed what you said about the negative in front of b. Which way does that reflect over x axis or over y axis?
Which way a negative in front of b? Which way does that reflect? Which axis? Yep. That's over the y-axis.
Okay.
I usually call it a horizontal reflection.
And then c is over the x-axis.
C is a vertical reflection, which you could say over the x. Okay, so here's one. It says, how can we graph log base 3 of negative x? We just did log base 3 of x. Right there. So if you do log base 3 of negative x, what is the negative going to do to that graph? Yeah?
It'd be reversing it, so it'd be in the opposite direction with negative numbers instead of positive.
Yeah, so can you give me the transformation?
It would be a reflection over the y-axis.
This is going to cause a reflection over the y-axis. So your graph, it's basically going to do something like that. So we're going to draw that and then describe the domain and the range. But I think if you can picture that reflection in your head, it makes the domain and range easy to think about. Okay, so how can log base 3 of negative x be graphed from the original? Okay, well, there's only one transformation. It's a reflection over the y-axis. So in this case, there is only one transformation. Reflect over y-axis. Now find the domain and the range. Okay, so we know what log base 3 of x looks like. We just looked at log base 3 with a negative x, and I'll show you how to type that in on the calculator too. So what's the domain going to be? Yeah. Right. The domain is going to be negative infinity to 0. Range you should never even really think about with a log function. What is the range? Yeah.
It's going to be all real numbers.
Yeah. Every log function has a domain of all real numbers. No matter what you do, you cannot change the range in a log function. Ever. Okay, they're always all real numbers. Find the domain, find the range, vertical asymptotes. Okay, let's go back to the. Actually, let me sketch it on the calculator so you can see what it looks like. I already have log base 3 of x typed in. All you have to do is put a negative in front of the x. So I'm going to do second, insert, negative. Right, and that's going to cause it to curve to the left. Let's see. Okay, what's your vertical asymptote there? Remember when I asked for a vertical asymptote, you have to give it to me a certain way, yeah?
Well, it's 0, but it doesn't touch 0, so yeah, I'm not gonna give it.
So how do you tell me a vertical asymptote or any asymptote?
X equals 0.
X equals. Vertical asymptote is always something equals. Well, vertical is always x equals. Asymptotes in general are something equals. So x equals 0. Okay. Why didn't the vertical asymptote move when we did the reflection? Shouldn't that have put it in a different spot?
If where it begins is the origin, it's not going to flip around. If it's like asymptote, was that like originally at like -2, it would have flipped over to +2, but it can't like flip over like that. It's at the origin, it's at 0. You can't do the negative or positive of 0. You can't switch that around.
Yeah. Okay, if you had shifted it left to right before you did the reflection, then the asymptote would have moved. But there was no left and right shift. That's it. Any question on that?
Kind of something about what we did last week, well, like the 5.4 thing.
Does it connect with this? No? Then let's hold off on that. So just so we can kind of keep the flow of stuff with this, and then we can look at that at the end. Yeah. Because there isn't really that much more. Alright, let's look at this one. How can log of 3 minus x be sketched from log x? Well, first of all, does the log equation I'm giving you this time fit the pattern with the ABCD? Does it look exactly like that?
No.
No, we should fix the log of 3 minus x. So it lines up exactly with the ABCD. What would we have to do? Yeah?
You just have to put x before 3, so it'd be negative x plus 3.
Negative x plus 3. Yeah, that's how we want to think of the log. All right. So now, how many transformations do we have? Yeah.
You have 2.
Yeah, there's 2. So it says, how can that be sketched? So it's 2 transformations. Okay. What's the first one? Yeah. So we're going to shift left 3. And then, yeah. Right, then a horizontal reflection, which is over the y-axis. So now, if I asked for the vertical asymptote, is the vertical asymptote going to stay in the same spot? So my question is it still going to be x equals 0? Yep.
No, because it's shifting.
Yeah, it's been shifted, right? It's going to look something like, okay, so here's your log. It's going to still curve. Let's just do log plus 3, right, inside. So if you do a plus 3, that's going to shift it to the left 3. So your vertical asymptote would be here, and then it would curve up like that. Now, with the negative, it's also going to take that, and it's going to mirror image it. So now, it's going to look more like that. So this is what your final answer would look like, and the vertical asymptote is now at positive 3 instead of negative 3. Okay. Any question on that? Yeah.
What is the ordering of the transformations?
The order of the transformations is the order.
Or is it literally just like left to right?
No, it's the order that alphabetical for the letters. The A, the B, the C, then the D.
Oh.
That's why I use those letters. So when you're describing, let's do one with all the transformations. Let's do like log. Let's go. -2 log 5x plus 3 minus 4. Okay, what's the first thing that you would write down there if you follow the order? Yep.
Left 3.
That's a shift left 3. Okay, so we got that. Then what's the next thing that we would do? Yeah.
Horizontal compression.
Yep. So that's going to compress it horizontally 5 times as much. If you wanted to stretch it horizontally, you would have done a 1/5. That would stretch it 5 times as much. So horizontal compression by factor of 5. So there's the next one. What's the third thing that would happen? Yeah? So vertical stretch by factor of 2. Yep. And the fourth transformation? Yep.
Would be transforming forklifts down. Or
Not yet. We are going to do that. There is a shift down 4, but there's something we have to do first. Yep.
flip it because of the negative.
Okay, give me a little more information.
It's I can't remember if horizontal or vertical.
That's vertical.
That's a vertical reflection.
That would be across the y-axis.
A vertical reflection, no, that would be over the x-axis. Yeah, that's up to down. So all your horizontal stuff is in here. All your vertical stuff is out there. So we got the vertical reflection, and now the -4 is shift down 4. So it didn't have every transformation, but it had quite a few. Now, once you have this many, it's kind of hard to imagine what that would look like in your head. I mean, you can kind of get an idea. But if we really want to get an accurate picture, we need to sketch it. So that's what we're going to look at now. So the most important thing that you need when you're sketching a log function is you need the vertical asymptote. Because once you have that, you know that the graph is either going to bend away from it to the right or to the left. Okay, it's going to do one of those two things. Now, let's think about the intercepts. Which characteristic of a log function, the domain or the range, is all real numbers? Yeah? The range. So what does that mean in terms of the three things I have right here? If the range is all real numbers, what's guaranteed to happen? Yeah?
Wait, what do you mean, like, what's guaranteed?
Well, if you have a continuous function and if the range is all real numbers, something is always going to happen. Yeah?
I mean, why? I mean, from what I'm understanding, why would always be a real number? Like, your range is what?
Well, range is y, but what does it mean if you have a function that's continuous and the range is all real numbers? Something is guaranteed to happen at some point. Yeah?
It intersects. What the intersect?
It intersects y.
At least one of them, like the y intersect.
Anyone else have a thought? Yeah? Well, we don't know exactly a value, but we do know that we're going to always have a what in a log function. That's what I'm asking. We're always going to have, think about it, continuous function goes up and down forever. So what does that mean is going to definitely happen? And for the other one, this is not guaranteed to happen. Yeah? It will be guaranteed to cross the x-axis somewhere. Every single log function will cross the x-axis because it goes up and down forever and it's continuous. Now, you are not guaranteed to cross the y-axis because you could have a log function like this that's never going to cross the y-axis. So that means you will always have an x-intercept. You may or may not have a y-intercept. Okay. Vertical asymptote, you will always have that. Okay. So how do you find the new vertical asymptote? Well, the only thing that can affect the vertical asymptote is stuff that's inside the argument, right? Think about if you have a vertical line and you shift it down 4. Would that be noticeable on a graph? If you had a vertical line and you shifted it up or down? No. By definition, a line goes up and down forever. So if you take something that goes up and down forever and you shift it up or down, you're not going to notice anything. If you stretch it, if it goes up and down forever and you stretch it by 2, it still goes up and down forever. So these values don't matter when you're finding the vertical asymptote. This is what matters. So to find the vertical asymptote, take what's inside the parentheses and set it equal to 0. That's how you find your new vertical asymptote.
It's pretty much the same thing with the polynomial.
Well, we did kind of the same thing with radicals, with
Yes.
square roots, cube roots, yep. We had to find the start point for square roots, and we set the radicand equal to 0. This is the same idea. Except we're not finding the start point, we're finding an asymptote. Now, once you have the asymptote, that's good, but you're going to probably need 3 more points. You know, maybe something like... And then once you have those 3 other points, you can make a good sketch. Now remember, when we draw a log, how many directions do log functions go from the asymptote? Like, do they go in one direction or do they go in both directions? Yeah.
There's 2 directions, like one's.
Well, in terms of like your the way that it's going to curve, like the domain.
Oh, yeah, it's going to go one direction.
It's only going to go in one direction. Right? When we think about like a cube root that had a center point and it went in each direction. Logs don't do that. So once you find your asymptote, you only want to check points on one side of it. Which side? Well, if you don't reflect it horizontally, you're going to check points to the right. If you mirror image it, you're going to have to check points to the left. Okay. So just a couple of reminders about how you find intercepts. So the x-intercept is where the y value is 0. Okay, think of the x-axis. Think of any point along the x-axis. Y is 0. The y-intercept is when x is 0. Think of any coordinate on the y-axis. The x value is always 0. Okay, so it's not really if you need more points, you do need more points. You need about 3 or 4. So pick 3 or 4 more x values. I would use the table on the calculator, plug them in, and then just use the table to plot the points. Remember, we have to make sure that whatever values we pick, we don't end up with an imaginary answer. So make sure that the argument is a positive number. Actually, not even positive. Yeah, positive. Can't be 0. It has to be positive. All right. So let's try a sketch. All right. So we're going to sketch log base 2 of 3x plus 5. Okay, so what's the first thing that I recommend you find when you're making this sketch? Yeah?
Vertical asymptote?
Yep, let's find the vertical asymptote. And it's kind of guiding you through it. It's telling you to find the asymptote. Well, you have to do that anyway to make a sketch. Okay, how do we find the vertical asymptote? Yep, so in this case, what will equal 0? 3x plus 5. So my vertical asymptote is going to be x equals
Negative 5 thirds.
-5 thirds. Which is about -1.6 for kilo. It's helpful to know the decimal when you make your sketch. Let's put that on our sketch right now. so negative 5/3, about negative 1.6. So we need a vertical line. Because it's an asymptote, it would probably help if I made it a little thinner. Okay. Yeah, I guess that's good. All right. Now, we can kind of figure out which way it's going to curve just by looking at it. Log base 2 of 3x plus 5. I'm either going to be checking values bigger than negative 5/3 or smaller. Which one is it? Yeah?
I think it's going to be bigger because it's all positive, so it's going to go arc over to the right.
Yeah, there's no reflection. If there was a reflection in a negative in front of the x, then it would curve to the left. Okay, but that's going to curve to the right. All right. Now, let's type that in. Remember, you do need your change of base formula to put that in because we don't have a base 2 log. So we got log 3x plus 5 divided by log 2. Right, our second table. And let's make sure it's on ask for the independent variable. And what I like to do first is let's check negative 5/3. Okay, and that should say error. It does. Now, if it goes to the right, then I should be able to plug in a number just a little bigger than negative 5/3. So let's take negative 5/3 and let's plug in something just a little bit bigger than negative 5/3. Works perfect. Even though it says those numbers are the same, if you look at the expansion with more decimals, they are different. Okay, so now we know what's happening. It's curving to the right. So what would be another couple x values I could use?
How did you get that negative 5/3 to work? The second one.
The second one?
Yeah.
I just typed in negative 5/3 and then I put like plus 0.00001 just to do a number a little bit to the right of it. So what would be some other good values? Kind of spaced out on my graph paper. Don't do like 1, 2, 3. That's too close. Space them out. Yeah.
2.
All right,
Close
2.
to 2.
All right, another one. Yeah. 5. Right, I'd go all the way to the end of the graph paper. We'll go to 10. We can do 0. Which intercept is that? Is that the x or the y intercept?
Y.
Yeah, that's going to be the y-intercept. Yep. So let's graph those points. So we got 2, just about 3.5. So we got that one. 5, we're at 4.3. 5, 4.3. Yeah. And then 10, just above 5. All right, so now I can see, I can put in the y-intercept. I didn't do that. 0, 2.3. Okay, so now I can see what the curve is going to look like. And I know that as I get close to the asymptote, the y value is going down to negative infinity. There we go. Any question on that? Now, what if I asked you exactly for that coordinate? I mean, I know it's maybe -1, it's around there. How would you find this coordinate exact? Yeah?
Plug it into the equation.
Plug in what number into the equation?
So, if you want us to find the exact y value, if you plug in 1 for x, then you would go to the equation keys, you could plug in 1 for x and then try to solve it, or you could just use the calculator and plug 1 into the table.
I can only plug in for x though. What
What
do I need to plug in to solve for this?
So, are you pointing at like when y equals 0, or are you
Yes.
Okay, so for when y equals 0, you can just set the entire equation equal to 0.
Yes.
Which means you're gonna find isn't that a different type of asymptote? So like when you set the entire equation equal to 0, you find like a vertical asymptote or a horizontal asymptote?
No horizontal asymptotes in logs, and for the vertical asymptote, that's when you set the argument equal to 0.
What happens when you set the entire thing equal to 0?
Then you're finding the intercept.
Uh,
Then you're finding where it crosses the x-axis.
But like yeah, you set the entire equation equal to 0, and then you can just solve it as normal. So you can do 2 to the 0 equals 3x plus 5.
Yeah, you could
Which
just
one?
change it to exponential form. 2 to the 0.
Equals 3x plus 5, meaning 1 equals 3x plus 5, and then basic math.
Bring that over. We get -4 equals 3x. So it crosses the x-axis at -4/3, or -1.3. That's exactly where it crosses. And now that we know that number, we could plug in -4/3 for x, -4/3, and that is 0. It's just it's doing it in scientific notation, and the calculator can't do the algebra that we did, so it's just estimating it. So the calculator is saying it's 0.0000 13 times, and then a 1/4. But it's okay. So any question on how we found the x-intercept? It wasn't necessary to graph it, but I may ask you in an equation, what is the x-intercept? That's how you do it. Okay, so there's our sketch. Find domain and range. Well, let's start with range. What's the range? All real numbers. And what about the domain? Yeah?
Negative all 4.66.
Yeah, what was our fraction?
Oh, 5, maybe 5 thirds.
-5/3, 2.
To infinity, to positive infinity.
Yep. And the vertical asymptote, well, we already found that right here. -5/3. Any question on it? Okay. Last question. So the last question involves a formula for earthquakes to figure out the magnitude on the Richter scale. And that's the formula. So R stands for the magnitude. That's usually the number that you hear reported when they describe an earthquake. And it's log of A over T plus B. Okay, what are all these things? Well, A measures how much the ground is moving in micrometers. So that's something they would have to tell you. It measures the movement of the ground in micrometers. T is what we call the period of the wave. So the easiest way to kind of imagine the period is if you're standing at a beach and you count how many seconds between waves coming in, that's the period. How much time it takes for the next wave to come by you. And in an earthquake, it really is a wave. Same idea, like if you drop a rock in the middle of a pond, you get a wave that comes out from the center. Well, that's what happens with an earthquake. A wave comes out from the center. And then as you move further away from where the earthquake started, what happens to the wave?
Does it get weaker?
It gets weaker, right? Just like if you drop, even if you take a huge rock in the boulder, drop it in the middle of a lake, if you're right next to it, you're going to feel a big wave. If the lake is 4,000 feet long, or it's like a mile long lake, by the time it gets to the other end, you might not even feel it. So you have to have a factor that accounts for the wave weakening as it spreads out from the center.
Is that a constant?
That's a constant. Yeah. A, T, and B are all constants. At least with the kind of problems that we're going to do. Okay, so what we're going to basically look at is a problem where we have conditions at the start of an earthquake that are constant. And then at a later time in the earthquake, they measure the same conditions again. Now, B would probably be the same all the time, unless the kind of soil that the earthquake is in is changing, which could happen if the earthquake is affecting like thousands, hundreds of miles. But we're going to assume that it's always the same type of ground. Otherwise, it gets complicated. So when we first have an earthquake start, we're going to measure what's going on. And at that point, the vertical ground motion was A. What is A? It would be a constant. We don't know what the constant is, but it was A. At a later point in the earthquake, it got stronger. The vertical ground motion changed to 10A. What I want to know is, what is the change in the intensity? What is the change in R if A increases 10 times as much? That's what I want to know. And what is the change in the magnitude if the ground motion becomes 10 times as much? Is R 10 times as much? That's what we want to see. All right, so let's think about the vertical ground motion. When is it stronger? Earlier on or later?
Early on.
So the earthquake is stronger earlier on. The ground motion is more at the beginning. What's the ground motion at the beginning?
Oh, later on it becomes stronger because it turns from A to 10 times A.
10 times A. So at a later stage, it's 10 times as much ground motion. So I want to figure out the difference between the two. And I want it to be positive. So would I do earlier on minus later, or later minus earlier on? Yeah. Yeah. So we're going to do later minus earlier. And what we're going to do is fill in the Richter scale equation. Okay, let's fill in everything we've got. So we got log. We're going to assume everything else that they didn't mention stayed the same. The factor that accounts for the weakening of the wave was the same earlier on and later. The period of the wave was the same earlier on and later. If multiple things are changing, that gets more complicated. So we're just going to change one variable. So we're going to have log of, what was my vertical ground motion later on? Yeah? 10A. Period, we don't know what it is, but it's the same now, and it's the same earlier on. We also don't know the factor that accounts for the weakening of the wave, but it's the same earlier on as it is later. Okay, same thing. What's the only thing that's going to change in this equation to represent earlier rather than later? Yep. Yeah, what's that going to become? Just A. Okay, so everything else stays the same, except the ground motion is going to be A instead of 10A. Okay, let's see if we can start to simplify that. And to be clear, I should go like this. I'm taking, that's later. What's in the second brackets is earlier. And the difference between the two is going to tell me the difference in the change in the Richter scale. So what's the first thing that I could do here?
Is there supposed to be a 10 in here?
Yeah, what's the
Oh yeah. I keep saying that. Yeah. A, not 10A. So this was later. That's earlier. Okay. What's the first thing that we could do here to simplify that? Yeah.
Would you change everything on the right side to negative?
Yeah, distribute the negative out. Because you're subtracting earlier. So you're subtracting everything that's in the earlier part. The later part, well, stays exactly the same. So now minus log A over T minus B. Okay, what happens now? Yep.
Quick question, doesn't the negative log make it imaginary?
No, it's outside. It's not inside the argument. Yeah.
Combine like terms.
And what happens when you start to combine like terms?
They cancel out
What cancels?
the B.
Yes, as they should, because the B was the same later and it was the same earlier, so it shouldn't have any effect on the problem. So it should disappear. Now, what else was the same earlier on and later? Yeah? T, that should disappear too. So let's see what happens. So now we've got log 10A over T minus log A over T. In each argument, what operation do they both have? Yep.
Division.
They both have division. When you have an argument that's division, you can split it into two logs. How does it split? Yep.
You can split it log 10A minus T and then B.
Yes. Log 10A minus what?
T. Oh, log T.
Log T. So you can split that up into subtraction. Log 10A minus log T minus whatever we do here. How does log A over T split up? Yeah.
Log A minus log T.
Log A minus log T. Okay, now we're kind of back at a similar point we were at in the first step. Okay, what do we have to do now?
Distribute again.
Distribute the negative again. Log 10A minus log T minus log A plus log T. Okay, what can we do now?
Combine like terms.
Combine like terms, and what happens when we combine like terms?
T cancels out.
What cancels?
T. Log T.
Log T, yeah. Negative log T plus log T. That was the same when the earthquake started. It was the same when the earthquake was later on. So the T shouldn't have any effect. It should disappear. Now we've got log 10A
Minus log A.
minus log A.
Can we make it a fraction?
Yes, let's put that back together now. So when you put that back together, it's subtraction. How does subtraction recombine? Yep. Yep.
Is it log 10A over A?
Yep. It recombines as a fraction. So log 10A over A. Now what's going to happen there? Yep. A's cancel out. Now we're left with something we can figure out. The log of 10. It's basically asking you 10 to what power gives you 10? Yep, 1. So if the ground motion increases by 10 times as much, what's the change on the Richter scale? It's a change of 1. Yep. If the ground motion changed by 100 times as much, what do you think the change would be on the Richter scale? It's a 2. So a magnitude 5 earthquake versus a magnitude 7, that's a 100 times change in the ground motion. Yep. So that's the answer. It's a change of 1. That's it. Any questions on that? All right. So we already did page 293. So I'm going to erase that part. Well, actually, we did the take home. We never did the 293. We skipped it. So tonight, it's page 301. I think it's maybe 12 questions or so. 11 maybe. Okay, and we'll take a look at that first thing tomorrow, and then we will start the trip.